Hello, everyone. Good morning. Thank you for coming to my talk. For a brief introduction of myself, my name is Zhi Zhu. You can also call me Derek. I'm a PhD student in chemical engineering department. My research group's name is Electrochemical System Laboratory. My supervisors are Dr. Anna Hanking, who is sitting there, and also Dr. Inyang Jiang, who is in the States, joining this meeting online. Today I'm going to give a presentation on my research project, carbon nanotubes production from CO2 via high temperature electrolysis. So as we know, global warming is a largely accepted fact now, and it's getting more serious. We can see the summer in London is getting hotter and hotter each year. So many technologies have emerged to mitigate the CO2 emission. Carbon capture utilization (CCU), along with carbon capture and sequestration (CCS), are very important CO2 mitigating strategies. The differences between CCU and the CCS is how to deal with the captured CO2. So CCS is to pump the CO2 captured into some geological reservoir, such as depleted mines, and also into the ocean. CCU, while it converts the CO2, capture the CO2 into some useful chemical feedstocks or fuels, such as formic acid, methanol, and carbon nanotubes. It's a very good method, a very good strategy, but there are some problems with current CCU technologies. So there are many systems which have been developed and studied to electrochemically reduce CO2 into useful chemicals in aqueous solution, such as methanol. However, there are extra CO2 emission and energy consumption, and the efficiency is quite low during the conversion process because the high over potential to drive the carbon reduction reaction in aqueous solution at low ambient temperature. And another problem the CCU technology is facing is the cost effectiveness. Most of the target products of the CO2 reduction are basic chemical feedstocks and fuels, such as methanol. It has low economic value, so it's not very economically feasible to operate CCU at a large scale, considering the high running cost and the low efficiency. So the life diagram shows a classic membrane-based electrochemical H cell. So the shape of the cell, it looks like an H. So this cell is used aqueous system to reduce CO2 into useful chemicals. Yes. So now I want to show the main target products we are doing now is carbon nanotubes. So what are carbon nanotubes? Carbon nanotubes are tubular structures consisting of graphitic carbons. There are mainly two types of carbon nanotubes. One is single word carbon nanotubes and multi-word carbon nanotubes. So the main difference is how many layers does the graphene layer, the graphitic carbons is. So it has amazing superior mechanical strength and high electric conductivity, also high thermal conductivity. So these properties enable it in many applications, such as nanoelectronics, lithium-ion batteries, drug delivery, and also as a catalyst. It's estimated to have carbon nanotubes is estimated to have a $20.3 billion global market in 2028. There are mainly three conventional carbon nanotubes production methods nowadays. One is electric arc discharge, and also chemical vapor deposition and laser ablation. Chemical vapor deposition, CVD, is the most commonly used method to produce carbon nanotubes nowadays. But there are lots of problems facing the carbon nanotubes application facing. One is a high cost, up to $114,000 per ton. And it's also difficult to control the quality, the size, and the structure of the carbon nanotubes using current method. So as I said, chemical vapor deposition (CVD) method is the most commonly used method to produce carbon nanotubes nowadays. It requires high temperature up to 600 degrees to 1,000 degrees, and it involves the process to catalytically decompose carbon precursors such as carbon monoxide, hydrocarbon, or ethanol onto a nanostructured transition metal catalyst such as nickel, iron, and also cobalt. So the catalyst availability has a significant impact on the CNT, the carbon nanotubes nucleation and the growth step, as we can see from the diagram on the left. So this is, we can see obviously, this is the catalyst layer, and this is the carbon nanotubes layer. Onto the carbon nanotubes is the NTC, we call it non-tubular carbons, which contains amorphous carbon or graphite. Because the carbon nanotubes layers forms here, so the carbon precursor is getting harder to reach out to the nanostructured catalyst. That's the reason why NTC layer is formed onto the carbon nanotubes layer. So there's a new method proposed to produce carbon nanotubes. That's also our method. It's to convert CO2 into carbon nanotubes via high temperature electrolysis. So it mainly contains several key steps, 3 steps. Firstly, we pump in CO2 or other CO2 containing flue gas into a molten electrolyte. The molten electrolyte always usually contains alkali metals or alkaline earth metal carbonates. And the CO2 in the flue gas will be absorbed by the alkali metal or alkaline earth metal oxide in the electrolyte to form carbonate ions. And then we apply a voltage between 2 electrodes. So the carbon nanotubes, carbon will be reduced on the cathode to form carbon nanotubes. And oxygen gas will be generated on the anode, and the CO2 free gas will be the outlet gas. So, and we need to keep the electrolyte in molten status. That requires high temperature, 600 degrees to 900 degrees Celsius. So to keep the high temperature, we don't actually need to use external heat to heat up the electrolyte to this temperature. Because the CO2 absorption is an exothermic reaction, so CO2 absorption will generate heat to keep the electrolyte in molten status. What we need to do is we need to make a well-insulated reactor to prevent any heat loss from the system. So this new method has the potential to significantly reduce the production cost on the order of $660 per ton. So we can say it's much less than CVD produced carbon nanotubes. And also with a net environmental benefits because we are consuming CO2 in this process. Another extra bonus of this process is this process can combine the CO2 capture and the CO2 conversion step. Usually CO2 capture and CO2 conversion are 2 separate systems, but this method can potentially combine the CO2 capture and the CO2 conversion into one system. So here is the proposed mechanism of the reaction. So there are mainly two different types of mechanism proposed. One is called, they are really similar to each other. One is called tip growth. So this is the net reaction is all the same for these 2 mechanisms. So the CO2 gas will be split into carbon in form of carbon nanotubes and also oxygen gas. So firstly, the CO2 will be CO2 dissolution. CO2 will combine with 1 oxygen ion to form carbonate ions, and the carbonate ion will be transported to the cathode and being reduced to carbon in carbon nanotubes form and to oxygen ions. So the metal catalyst will facilitate the nucleation of the carbon nanotubes and stay on the tip of the carbon nanotubes So the carbon nanotubes will grow keeps growing on the tip of the carbon nanotubes along with the metal catalyst. And also the oxygen ion will be oxidized to oxygen gas on the anode. So this is a different mechanism, but it is similar. It's called root growth. Instead of the metal catalyst that stay on the tip of the carbon nanotubes, so it facilitates the nucleation of the carbon nanotubes. It stay on the substrate, which is the cathode. It stay on the surface, so the carbon nanotubes grow from the bottom, from the root of the carbon nanotubes. Yes. The net reaction and all the reaction are the same. So this is the experimental setup we used to investigate the carbon nanotubes production from CO2 using high temperature electrolysis. The main component of our experimental setup is the furnace, as we can see from this picture. So it's the vertical tube furnace. We put an aluminum crucible inside of the furnace, and we use this called alumina tubes, thin alumina tubes, to wrap the silver wire to connect the two electrodes inside the alumina crucible. And we use carbonate salt. We put carbonate salt inside the crucible and using the tube furnace to heat it up to 800 degrees to make the carbonate salt melted. And in the future, we would like to pump in CO2 into the electrolyte to enable longer duration electrolysis to generate more carbon nanotubes. And also we connect the silver wire with the potential stat to carry out any electrochemical measurements. This yellow part is a tray. It shows here it's filled with sand to catch any molten salts in case of the crucible is broken. So safety is always the first. Yes, so we have two electrode configuration now. Both of them can achieve uniform electric field in the electrolyte. Firstly, we use two metal wire to make the metal wire into spiral disc shape, and we put them facing each other. We put the anode on the top and the cathode on the bottom. The reason why we're doing that is because there will be oxygen gas generated on the anode. So if we put the anode at the bottom, the evolving oxygen gas in forms of bubbles may have influence on the cathode, on the carbon nanotubes produced on the cathode. And the second one is we put a central metal rod in the center and use a spring-like wire anode to surround it, the central cathode. In this one, it's easier to peel off the carbon nanotubes produced on the cathode because it's a central metal rod. It's easier to remove the carbon products. And in the future, we would like to inject CO2. So we have a CO2 bubbler here at the bottom. Here is our experimental procedure. So firstly, this picture we use nickel wire and iron wire to make the electrodes. So the nickel will work as the anode and the iron will be the cathode at the bottom. We use alumina tubes to wrap the silver wire. It connects with the nickel and the iron electrodes. And then we immerse the electrodes into 0.5 molar hydrochloric acid to remove any oxide and the impurities on the surface of the electrode. Then we set up the cell, the electrochemical cell. We put the electrode into the central small crucible and bury it with lithium carbonate salt, 99.9% pure. And we put the whole thing into a furnace and heat up to 800 degrees at a ramping rate of 3 degrees per minute. Then we apply a voltage using the potential stat between the two electrodes at a current density of 200 milliamps per square centimeters for 3 hours. And then we take out the electrodes. We can see some carbon products generated, produced on the cathode, the bottom iron cathode. And then we use 0.5 molar hydrochloric acid again to wash the electrodes to remove the carbon. We use section filtration then to filter the suspension to get the carbon products and dry it under the airflow. Yes. So here we did some thermodynamics prediction using the data we obtained from NIST. So at around 800 degrees, the thermal neutral potential is around 1.5 volts. Here is the so we carry out the electrolysis at constant current to keep the current density, the initial constant density at 200 milliamps per square meter. Because as electrolysis carries out, the surface area of the electrodes is getting bigger, so this is the initial current density. But we keep the current, the overall current constant. We measure the change in the voltage. We can see it's ranging from 1.92 volts to around 1.75 volts. So we also study the corrosion. So we put the electrodes in the crucible and heat it up to 800 degrees. But instead, we don't apply any voltage. We apply 0 volts to measure the current. So that's the corrosion current. So we can see for 3 hours, not 3 hours. So 12,000 seconds. Oxidation reactions happens on the iron wire electrodes. We can see the current is negative because the iron wire was connected to the counter electrode and the reference electrode. Nickel wire was connected to the working electrode. So we can see some oxidation reaction happening on the iron electrode, and some reduction reaction happen on the nickel electrode. So the corrosion current it decreases as oxidation layers forms on the iron electrode because this increases the resistance, so the current getting lower. So we carry out electrolysis using 4 different setups. We mainly use iron, 99.9% of iron electrodes and nickel electrodes. We mismatch each other. So we can see for iron, we use the iron as a cathode and iron as an anode. Only a small amount of carbon nanotubes forms on the electrode. Most of the carbon materials generated on the cathode is amorphous carbon. If we use nickel as the cathode and iron as the anode, so we can only generate amorphous carbon. No carbon nanotubes was observed. The best performing one is we use iron as the cathode and nickel as the anode. A wide range of carbon nanotubes were observed, including carbon nanotubes and also carbon nanofibers, and also other carbon nanoparticles. But the majority is carbon nanotubes. So if we use nickel as both cathode and anode, no obviously carbon products formed on the electrode. So we did some SEM. On the products we have and also the commercially available carbon nanotubes. So this is the SEM images of the carbon nanotubes produced by CVD. We purchased it from Sigma Orange. The diameter of the carbon nanotubes is around 20 nanometers. We can see the fiber is quite long and it's quite uniform. Here is the SEM image of the carbon product synthesized via our method, molten carbonate solid electrolysis, using the iron as the cathode and the nickel as the anode. The initial current density 200 milliamps per square centimeters. we can see a white. We can see some thin fibers here, and also thick thick tube there. And also we observe some carbon nanoparticles. So the diameter is around 50 nanometers, compared with the 20 meters diameter of the CVD synthesized carbon nanotubes. Here's SEM images of the carbon products since using the same current density, but with iron as the anode, nickel as the cathode. So we switched the two electrodes. So no carbon nanotubes was observed, just amorphous carbon. Here we use iron electrodes as both the anode and the cathode. So we have some very short carbon nanotubes and also carbon nanoparticles and short nanofibers. But majority is amorphous carbon. We also did some TEM on our products and also the commercially available CVD carbon nanotubes. So this is the TEM images of the CVD synthesized carbon nanotubes. You can see its hollow structure in the center. So SEM can only see the outside of the carbon nanotube, but TEM can see whether it has a has a hollow structure. So whether it's carbon nanotubes or carbon nanofiber. Yes. So this is the TEM images of our products synthesized by the best electrode configuration using iron electrode as a cathode and the nickel wire as the anode. You can see we also generated carbon nanotubes because it has a central hollow structure, as the TEM images suggest. Yes, we also have some solid. So this is no hollow structure, so it's carbon nanofiber instead of carbon nanotubes. So here is a conclusion. So as a result, we successfully synthesized the multi-watt carbon nanotubes along with other carbon products such as carbon nanofibers, carbon nanoparticles via high temperature electrolysis in lithium carbonate salt. We also investigated different combination of the iron and the nickel electrodes. But we have some problem with our current research. One is the reactor is open to the air, so resulting in the oxidation of the oxidation and the corrosion of the electrodes before we carry out any electrolysis. And also the reaction mechanism and kinetic have not been very well investigated. And for now, we're using a 2 electrode setup instead of a 3 electrode setup. So we don't have a reference electrode now to form a 3 electrode electrochemical cell. So future work, one is we want to investigate more about the nucleation and the growth mechanism of the carbon nanotubes in molten salts using a 3 electrode setup. We want to introduce a platinum reference electrode, platinum wire as a reference electrode to well study the reaction kinetics. And then we want to introduce CO2 into the reaction system to study the regeneration of the consumed carbonate salts. But this requires us to have a closed system, not to open to the air. So now we are working on that. And also in the future, we would like to investigate more reaction parameters impact, such as the temperature, the electrode materials, and also the current densities impact on the carbon products we can get. Yes. I want to thank my supervisor, Dr. Anna Hanking, and Dr. Inyang Jiang for supporting me to carry out the experiment and this research project, and also other group members in electrochemical system laboratory, my group. Thank you very much. Please feel free if you have some questions. Express.
Yeah, I'm particularly interested about the job of the iron as a cathode?
Yes.
Do you think it is because iron is a better catalyst for the reaction?
Yes. So I think our method is there's something similar with the CVD method and also our method, the electrolysis in molten carbonate salt. So in most of the published articles, journals, it's reported that iron is a very good catalyst in the CVD method to produce the carbon nanotubes. I think things similar happens here in the electrochemical cell.
So, I mean, in CVD, most of the catalysts are in the form of nanoparticles, right?
Yes,
so if that's the case, maybe, I don't know if it's like changing the topography of the iron wire can have a huge effect on how much of the CNT can be formed on the working electrode. Maybe like make it more porous is better.
Yes, that's a very good point. In the future, we would like to investigate if we can generate or produce some nanostructures surface on the iron electrodes. Maybe in that case, it's better for the nucleation of the carbon nanotubes. Definitely, thank you. That's a very good.
And also, what's the yield? I mean, how much percentage is CNT and how much percentage is the amorphous carbon in that case?
So we don't we haven't done any yield test yet, but as we can see from the SEM image, so if we use the iron as a cathode and nickel as an anode, we get a wide range of carbon products, including carbon nanotubes, carbon nanofiber, and also amorphous carbon nanoparticles. And we, for now, actually, I don't have a good method now to carry out any yield test on the generated products. Yeah.
Thank you very much. Very nice talk.
Thank you. Yes.
Very nice presentation. Thank you very much. Just to follow up on the question my colleague asked. So I'm just wondering, because you mentioned you do have some oxidative corrosion on the anode that you observed. So I'm just wondering which one do you think is the rate limiting step for your electrolysis? Obviously, you have a half reaction of the reduction of carbon dioxide and the oxidation of oxygen. So which one do you think is the rate limiting one?
That's the reason we want to, in the future, we would like to introduce the reference electrode, the plug-in wire as a reference electrode to study more about the kinetics, see which reaction is more limited. So now we don't have accurate data yet to support any theory or statements. That's a very good point. And also in the future, we would like to study the efficiency of the reaction, the current efficiency, because we know at higher temperatures, the overall potential required is less, but we want to study like how much of the current, the energy input is converted into carbon nanotubes instead of amorphous carbon. I'll see you.
Hi, it's really nice talk, thank you. So I'd like to ask if I understand correctly, so the carbon was formed at the surface of the cathode. So how do you constantly use your techniques to produce your carbon nanotubes? Because when your techniques go to a certain degree, there's already a layer of carbon tube on the surface of cathode, then this gonna be impede the carbonate to be contact with your cathode, which gonna impede the direction. So I mean, how can you calculate this?
So you mean in the future, if we carry out this method in industrial large scale, how to constantly produce carbon nanotubes? I mean, how to control the length of the carbon nanotubes. According to the published literature, they said if you control the current density in the end, after you have a desired length of carbon nanotubes, you can use a higher current density or different voltage to make the carbon nanotubes peel from the surface of the electrodes, and then more new nucleation site forms on the cathode, and the carbon nanotubes can grow. So it will be kind of a batch process, I think.
Okay, so which means you don't need to get it out and like the method you said, to wash it out and then to.
Definitely, we don't want that at industrial scale.
Okay.
That will be, it requires lots of acid, and also it's definitely not environmental friendly. We doing that. So in the future, I imagine we can have a better method to separate the carbon nanotubes from the electrode, and also there should be a mechanism to collect the carbon nanotubes in the electrolyte, to remove the carbon products from the electrolyte when the electrolyte is still in molten status instead of is solidify, recrystallized.
I see. Thanks.
Thank you.
Someone's asked, when you synthesize a mix of carbon tubes and fibers, are they separable, and if so, how?
Sorry, I do.
So it says, when you synthesize a mix of carbon tubes and fibers, are they separable, if so, how?
Yeah, so now we produce the carbon nanotubes and along with our carbon nanofibers and carbon nanotubes, but now we don't know how to separate or separate them, or how to purify the carbon nanotubes we produced. Yes.
Can I supplement that answer? So the idea is that we're trying to find first of all, we try to prove that the process actually works in the first place. And then the purpose of the work is to find conditions that selectively produce one type of nanostructure so that you don't have to go through the separation process. To do that study, that's why we started to try and change the applied cell potential and to measure current as a result of it to see if it shows up anything interesting about the mechanism. And that's when we discovered by accident that when we applied a potential difference of 0 volts, that actually there was a spontaneous current flowing and that we had corrosion in the system, which would in the future have to be controlled. So there's a lot of things that we're still learning about it, but the idea is to selectively grow one type of nanostructure so that the separation isn't a problem. And just about your question about which one is the rate determining step, I mean, the point of applying a constant current is that you're not limiting the rate of anything because you're imposing it. Presumably, the carbon reduction from oxidation state 4+ to 0 will involve 4 electrons, and we have no idea which one of those transfers is rate limiting. But at the moment, yes, we're just trying different conditions. In principle, it would be better to apply a fixed potential rather than a current, but at the moment, we are unable to understand the changes in the current enough, so we're still probing. Yeah, still early days.
Yes.
Yes. When you change the actual materials and it gives you different carbon materials, and have you got any idea on how this actual material affects your morphology of the carbon materials?
Yes, as I mentioned, I think our method, this is my hypothesis. So as our method, the method to produce carbon nanotubes in molten salts, I think the mechanism should be similar to CVD method. So for CVD method, what they will do is that they heat up the substrate, which usually iron, like I said, for example, iron, to high temperature in oxygen, and get some part of the surface of the iron substrate get oxidized, and then they use hydrogen gas to hydrogen gas in the hot chamber to reduce the iron oxide back to iron again. In that case, the substrate will be iron nanostructures. So in this case, I think, so because we studied, the reason why we studied the corrosion of the cathode of the iron electrode, I think that because the iron get oxidized during the heat up process, so that forms some small maybe nanoparticles or nanostructure on the surface of the electrodes. In that case, it forms the nucleation site to facilitate the growth of carbon nanotubes. So I think that's the case. So that's the reason why if we switch these two, because during the heat up process, the iron electrodes is already get oxidized. the nickel, maybe the nickel electrode is not, oxidized as desired, so that didn't give out the carbon products, the carbon nanotube products. Yeah, that's my hypothesis.
All right.
Yeah.
So just follow up on the clarification. So do you think it's the redox potential of those material that makes a big difference? And what would be the criteria when you're trying to decide an electro material in the future?
You mean in the future, which kind of materials?
Yeah, when you design your electrode, what's the criteria?
What's the criteria? To be honest, I want to investigate more potential of good material, good substrate for CVD. So kind of like nickel, cobalt, and iron, and to alterate the nanostructure on the surface of the electrodes. So because I think these two are similar, so I want to like using more materials good for CVD. So put it here. Yeah.
Do you observe any metals on the carbon nanotubes when you analyze them? I forgot.
No, we are going to use XDS. Yes. XDS to see the EDX. Sorry. Yeah, EDX. Sorry. Yeah.
Sorry, it's just, but I think in terms of the detecting iron, EDS might be not
Very good.
sensitive enough, because that means the majority is gonna be carbon.
Yes. And another thing.
I mean, in the literature, I think the more common method is ICP mass, and maybe just oxidize all of it into the strong acid and did it and measure the iron content. And I think that might be more
Using SCP MS.
Yeah, ICP mass. That might be a more fast. Sorry, it might be, so I came across some of the literature before, because I also concern the content of iron in my CNT work. So I think that might be better. Yeah, I even thinking also doing the same thing on my CNT. So yeah.
And also because the post-treatment of our products, we use hydrochloric acid to do the post-treatment. In that case, maybe it removes some part of the iron in the samples already. So maybe in the future we can just remove the carbon, the products from the electrodes physically, not chemically, and using SAP MS to see whether there are some metal ions inside the products. That's very good. Thank you.